How we doing, guys? Hopefully you guys are doing well. This is Ron Alexander. I wanted to put this video together and just as kind of a test, kind of testing the waters. Today is January 1 of 24. It's Monday. I stopped into work to do a little lab prep and kind of put some stuff put some stuff away that I had out for the week. But I just got thinking, a couple of weeks ago, I taught an electronics class for a group of technicians in the Oswego, or excuse me, in the Cortland area. And one of the things came up, and I keep running into this as I teach electronics classes for service technicians, is and I'm not exactly sure what to call it, but what it is there's a lot of technicians that are working in the field that are doing automotive electrical diagnosis. And they're utilizing full meter functions. They're doing what they've been taught to do. They've been testing for voltages. They've been testing for resistances. In some cases they've been doing amperage readings. But there's still a kind of a misunderstanding or a disconnect between the use of the meter and like intermittent high resistance faults. I mean, in a perfect world, if a wire was open and you measure the resistance across that wire, you would find that the wire was open. You'd be able to identify it and find it. If you were measuring voltage in a pin and the wire was open, you would have no voltage if that was a power supply to a control module. If you had an open ground wire and you had a wire disconnected on the ground side, and you measure resistance between that wire and ground, you'd see that it would be open. And that's what we've taught. That's, fundamental electrical diagnosis. But the reality is, on our cars, especially cars that we see in the Northeast with our salt usage on the road, we're finding that we are getting circuits that are corroded, and the way the circuit functions when it's corroded is significantly different in some cases when it's loaded to when it's not loaded. Now, it's a very difficult concept to understand, but the way I described it to my students, the way I've been describing it for years, is if you have current flowing through a wire and that current is relatively low, in some cases that corroded wire will allow that current to flow and allow that circuit to function fine. But if you increase gradually, or in some cases, just increase, it could be instantaneously, you increase the current flow through that corroded wire, the corrosion will actually create some resistance, which will create some heat, which will actually increase the amount of resistance in the circuit. So you'll have a circuit that may function fine, and then all of a sudden start not to function. And that resistance becomes more predominant as the current drives through the circuit, or as the component is being powered up, or whatever the device it is. Could be a heated seat, could be a rear defroster, could be a fuel injector, it could be anything. So what I found is, with most technicians, by utilizing the basic fundamental skills of just measuring voltage, just measuring resistance, just measuring amperage, may not be drawing to the proper conclusion, or the identifying where the problem exists in the circuit. So what I've been trying to do over the last number of years is try to get students to understand the concept of voltage drop. Now, what voltage drop is as current flows through a circuit, if there's resistance within the circuit, the pressure of that voltage, because remember, voltage is a measurement of electrical pressure, as the pressure in the circuit reaches the resistance, the pressure will drop across the resistance. So if there's a corroded connector that's feeding 12 volts to a pump or a fuel pump, that corroded connector may ohm out fine if you disconnect the circuit. If you unplug the fuel pump and measure voltage at that wire that feeds the fuel pump, that may still read 12 volts with the DVOM because the circuit is simply unloaded, meaning that there's very little current flowing through it. And that's a difficult concept to understand, but one of the things I teach my students is the pressure in the circuit will build to the open. So if you disconnect the connector, you've created an open. So what's actually going to occur is that pressure is going to be the same throughout the circuit up to that open, even if there's resistance within the circuit. I feel like I'm about to sneeze, so if I do, excuse me, I'm sorry about that. Didn't mean to do that to you. But that's, the concept I need to try to teach my students is understanding electrical diagnosis with a circuit that the resistance within the circuit can vary as the circuit functions. Again, it's a difficult concept to understand, but once you understand, you fully grasp what's going on in the circuit, it makes that misdiagnosis that you did, 3 years ago, though it's been driving you crazy, make more sense, because voltage is a measurement of electrical pressure. So if there's pressure on a conductor and that conductor has resistance in it, if you disconnect a connector, the pressure is going to build to the open, and now you're going to have voltage right to that point. And you can measure that connector and measure 12 volts of that connector and say, yeah, that's got to be a good wire. Or worse yet, if you suspect that there's resistance in the circuit, technicians will disconnect both sides. Like we tell you, when we measure resistance, you want to disconnect and isolate the circuit, make sure there's no other power, no other chances for current flow. And then you measure resistance from one end of the wire to the other, and there's very little resistance being shown in the meter, or none. And you suspect that wire's got to be good because there's no resistance. I have 12 volts at the end of the wire has to be good. And it's just not true, because if you have a single strand of copper connected and you measure the resistance on either side, that single strand is going to give you very, very little resistance whatsoever, because your ohm meter doesn't produce that much current flow. So it's not a really good test. So over the years, we've come up with devices. I mean, a lot of the old timers, they would get a sealed beam headlight. And what they would do is they would try to light up a sealed beam headlight with a power supply to see if that's nice and bright. And what are they doing? They're actually loading the circuit, pulling current through the circuit to see if the headlight's dim. And if the headlight's dim, then obviously you have resistance within the circuit. So a lot of the old timers, they and I shouldn't say old timers, the younger guys too, will put jumper wires on either side of a sealed beam headlight and go in there, and that's fine. I mean, that's a good way of doing it. But I think a far superior way of doing it is to analyze the circuit as current is flowing through the circuit, as the circuit is powered up. Analyze the circuit, measure the voltage drop across those conductors. So if you measure your power supply voltage at 12.4, and then the connector that's being powered, your fuel pump, goes through a relay, and a relay contacts are closed, and you force them close with the scan tool, and you measure the voltage to that pump while the pump is connected, and you measure the voltage as 12.4 volts, that means there's no drop from the power supply to the wire going into that motor. And that's a pretty good indicator that that's a good circuit. That's as long as you've got current flowing through the circuit. Now, if you were to measure the voltage at that connector going into the fuel pump, and you measure, let's say, 11.8, and your battery voltage was 12.4, that means you've got a drop. I don't know what the math is, but you got a drop in a certain amount of voltage across that conductor, and that doesn't seem acceptable to me. You've got a measurable voltage drop. Some will say half a volt is acceptable, or 4/10 or 3/10. I don't know. I don't want to give you a number, but I mean, I'm going to say that there is a voltage drop in that circuit. There is some resistance in the conductor and the switch contacts and the relay, whatever. The less, the better. So now, if we were to monitor that circuit and let that pump run for over time, and maybe we turn on a couple other devices on the car, maybe we turn on another couple of relays, maybe we even start and run the car, and we notice that voltage, that drop, or that voltage going into your motor, starts to decrease and decrease more, or just changes, goes up and goes down, and goes up and goes down, depending on things are turned on and off. Your source voltage still remains the same. Maybe you got a charging system that's on, and maybe that's going to be your new source voltage. But we can look at that and analyze that. And I tell my students to spray the circuit down with salty water, take a compressed air gun and blow it across the harness and make it seem like it's going down there. A lot of people grab the harness and they shake it, and they do that, what they call the wiggle test. And unfortunately, you do a wiggle test, and sometimes you can push the connector together and everything works fine. So I tell them, just take a compressed air line and blow on the harnesses, and that blowing will simulate the car going down the road. And if that voltage starts to drop more, we can actually call that high resistance within the circuit. And then you can, you'll have to analyze that, just keep stepping through the circuit. So that's called voltage drop. It's been used for years, been taught for years. A lot of instructors go in and they show you how to go parallel across the devices, across the connectors, and that tends to confuse some people. So I usually tell my students is take that, because you only have, with these classes, I only have 3 hours to teach what I do in 15 weeks in a college class. But take that negative lead and put it right on the negative battery terminal. Take your positive lead and jump through the circuit. Starting at the fuse bank, here's your source voltage, or even at the battery, looking at the battery, you get your source voltage, go across the battery terminal, jump through the circuit, come out to the load device, see that you've got source voltage to the load device. If it's less than source, your problem is on on that feed side. It's going to be on the power supply battery positive side. If it's less than source at the load device. And then I want you to immediately go over and check the ground. I mean, leave that negative terminal right on the negative battery terminal. Take that positive lead and take it to the negative lead of your fuel pump. Take it to the ground. If you're on the ground wire of any circuit and there's voltage there, there's pressure there, that means that there's got to be resistance between that ground wire that you're attached and the ground wire that your other lead's on. Because remember, voltage is a measurement of electrical pressure. If I continue that definitions, it's electrical pressure or potential of an electrical charge. So if you've got your negative lead on the negative battery terminal and your positive lead on a known good ground or suspected good ground, and you see voltage, that means that you've got resistance in that circuit. Again, that's voltage drop. And that test is only valid when there's current flowing through the circuit, or at least attempting current flow. You got to try to turn that circuit on. But that's voltage drop. And I think that's a really important concept for technicians that are trying to isolate resistances in electrical circuits, understanding how to do a good, solid electrical voltage drop test. So I'm going to skip out of here for a second. I'm going to go into a little circuit building thing. I'm going to try to share my screen, and hopefully you guys can see what I'm doing here. So I'm just going to come in here and I'm going to click on share screen. And you guys should be looking at my screen right now. And I think I can do this. There we go. This is the one I want to share with you. So I'm into what they call Tinkercad right now. And what Tinkercad is a little free software, circuit building software that you guys are actually, it's not really a software. You got to be online to do this. So it's a web-based program, but it's called Tinkercad. Now you can log into Tinkercad, create an account, play with this as much as you want if you want to. But this is called Tinkercad. Once you go into Tinkercad, you're going to select Tinkercad circuits. I'll actually step out of here for a second. Let me just go back. We'll go in and see what it looks like. But once you create an account, your account's created, you click on your little icon up here, because you can put your name in here. You're going to select New Design, and you're going to select Circuits. Okay. And then from down here, you're going to go ahead and build the circuit. Now, what I recommend you do is go ahead and select all circuits, or all components. So all this stuff on the right is going to be available to you to build. So what I'm going to do is I'm going to create a really simple circuit. Keep it very easy. When I teach the class, I tend to get a little crazy building circuits. But I'm just going to go ahead and bring a 9-volt battery up, and I just like to level it out so it's so you can see it. So I just clicked on the battery and brought it out here. And I'm just going to do a 1 bulb set. So I'm just going to grab a single incandescent bulb. And there we go. Okay, single bulb. I do want to put a control device on there. So I'm going to try to find a switch. Should be a little slide switch in here somewhere. Instruments, like that. I'm going to go up a little higher. It's probably up here in control devices. I think I'm getting close. And there's a little switch. I'm going to put a switch in there. So there's my little switch. Okay, what I'm going to do is I'm just going to wire this up, and I'm going to use red for battery positive. So I changed my wire color to red. So I'm going to bring my wire up here, and I'm going to connect it to the terminal. And then I'm going to take, once I go through the terminal, I kind of want to change this to green, just so this will just indicate I'm into a different control circuit. So the green will be kind of the control circuit. And then I'm going to go and wire this up for ground. So I'm going to use black. So that allows me to do just a basic series circuit, just like that. And there it is. Now, the cool part about this is actually considered what they call a circuit simulator. So you can build a circuit and then you can hit start simulation, and this will actually turn it on for you. So I can control the switch, I can turn it off, I can turn it on. So the common connector is the center one on the switch, and then you've got the two unique outside terminals. So right now I've got terminal 1 and terminal common connected. If I click on that, now I've actually opened the circuit. So you can actually come in here, you can do all kinds of elaborate circuits. So there's your basic circuit. So what I'm going to do is I'm going to do just some fundamental testing on this. So I'm going to grab a voltmeter. And that's one nice thing about Tinkercad is you can actually create put your own test equipment on there, and you don't have to have a bunch of very expensive meters and jumper wires running around your bench. So I'm just going to take this negative terminal. I'm going to bring this all the way over here, and I'm going to take it right back to the negative terminal. Okay, and then I'm going to take my battery positive, my positive lead. This is going to be my jumper lead, my test equipment lead, and I'm going to come around here, and I'm going to measure voltage going out of the battery. So what I want to know is I want to know what my source voltage is right now. Right now, my 9-volt source voltage, this is the amount of source voltage that's being applied to the bulb, or should be applied to the bulb, is about 8.73 volts. Okay, and when I turn this off, you'll notice it rises a little bit. So the circuit simulation is actually showing a little bit of drop across your power supply. I don't want to be confused by that. That's not a problem. That's just, the amount of current that's flowing through this big honking bulb is drawing that battery down. So it's actually, they're actually, giving you a little bit of background information. So what I want to do is I want to measure voltage to the load device. Okay. So, again, the negative lead for my meter is going to be left in the negative battery terminal. So I'm going to move my positive lead. Okay. I'm going to stop my simulation. And then I'm going to take the positive lead. And I'm going to now move this over to my first load device, which is my only load device in the circuit, which is right there. And I'm going to go ahead and start simulation. Now, ideally, the voltage at this point should be my source voltage, which I think we saw earlier was slightly under, under your 9 volts. So it did drop a little bit. So that little bit of drop will probably be across the switch contacts themselves. Okay. So I'm going to go ahead and move this again. Let's bring this back. I'm actually going to read this right across. I'm going to measure it right to here, coming into the switch. Okay, you got to line it right up with that terminal. There we go. I'm going to start simulation again. And oh boy, 873 is what we got. I think that's what we had, the source. So let me go back to this again. And again, I'm just going to confirm that I got 873 or very, very close coming into my terminal. And at that point, I'll start my simulation, 873. Okay, so that tells me that there is no voltage drop through this part of the conductor. Okay, now if you were to monitor this over time and you were to spray this switch down with a little salty water, maybe you put a heat gun on this, or maybe you blew some cold air on it, or compressed air on it, or you wiggle things around, and that stayed at the 8.73, just what your source is, I would call both of these conductors, the switch and the conductor down to here, I would call that as a good circuit. Okay, now what we can do is if we want to test and verify our ground is good, we're going to take our battery positive lead, and I'm going to take this around, and I'm going to put this on the ground side of the circuit, just like that. Start my simulation again, and you're going to see 0 volts. Now, a lot of people look at this and they're like, wow, well, why would I ever do that? Well, if there was any number here greater than 0, that would represent resistance in the ground. So I'm going to monitor that 0 volts. I'm going to monitor that for a while. I may actually spray this harness and hit it with a heat gun and wiggle it around, hit it with compressed air, do whatever I got to do. And if this circuit stays right at 0, I'm going to call that a good ground. So to sum this up, if you have to actually follow a diagnostic procedure, or if you actually have to go in here and actually have a flow chart, I guess some technicians, they just need to know, hey, what do I do next? If your voltage drop is greater than 0 on the ground, your problem's on the ground side. If your voltage drop coming to the feed side of the bulb is less than source, your problem's on the feed side. Okay, so those are the two. If you're going to create a little chart and you want to draw something in your toolbox, that's what you really want to do. And that's another thing I find with electronic diagnostics. We don't do enough of this to really get really proficient with it. We don't get into a situation we just practice enough. So for you guys, I want you to use this little tool. Now let's simulate a fault. Okay. So what I'm going to do is I'm going to throw a little corrosion. Now, unfortunately, I can't. And I'm not going to do fixed, or excuse me, I'm not going to do a variable resistance corrosion. I'm just going to do throw a resistor at it. I probably got something in here I can find. I should get a little bit more proficient at finding these things, but somewhere in here has got to be a resistor. Where are my resistors? There they are. That's a diode. Here's my resistors. So I'm going to take a resistor. Now I'm going to play around with the size of this thing. I'm going to drop it down a little bit. It's at 1,000. I'm just going to bring it up to, let's say, 500 ohms. Okay, so we're going to have a 500 ohm resistor. And I'm going to put this resistor at first in the feed side of the circuit. So I'm actually going to do this in the green wire. So this is going to be a green wire or a feed circuit corrosion. That's what I'm going to simulate here. So I'm going to bring this down, bring this into here, and I'm going to take this, wire this back up to the bulb. So there we go. So I'm going to start my simulation. Now, the concern I have with the simulation, this bulb isn't quite as bright as it was a second ago. It's not quite as yellow. To look at this electrically, I'm going to stick a voltmeter up here. So I'm going to drop down here, stick a voltmeter in. Okay, and again, I'm going to use my black lead for my negative lead for my voltmeter. And again, I'm bringing this all the way, this all the way over to ground. Again, that's the best ground, best wire on the car. Or the only known good ground on the car is the actual battery terminal. So battery terminal ground. So now I'm going to take my red lead and I'm going to measure right at the load device first. And this is my thought behind it. There may be multiple locations to take this test through the circuit. Some people will say, hey, I'm going to check the fuse first, or I'm going to check the switch first, or I'm going to check the connector underneath the dash first. If the load device is the easiest thing to get to, I usually tell my students to start at the load device. So I'm going to pull the headlight out of the bezel, or I'm going to pull the PCM or whatever I'm dealing with forward, or whatever I'm looking at. So that's my load device. So I'm going to start there. And again, it's up to you. You take your own, choice on that. So I'm going to go ahead and start the simulation again. And at this point, we're going to see a significant drop in voltage. Now, while I'm doing this, I'm going to change my resistance, and I'm actually going to bring this down to 50. Okay, so that's a little bit more realistic resistance in the circuit. So in this particular case, I have 50 ohms of resistance. But what I've essentially done is I've essentially dropped my voltage. So at this point right now, my voltage coming into my bulb is less than source. So if it's less than source, my problem will be on the feed side or the source side of the circuit. If I get out of here and I check this on ground, I'm going to check this on ground to see how this effectively changes my ground. And I'm going to go and start the simulation again. And you'll see this hasn't changed the ground at all. So the ground is not changed. So in this particular case, this part of my schematic is fine because I'm reading 0 volts. This part of my schematic is bad because I'm seeing a voltage drop. Now, if you want to, we can try to figure this out because you're not going to know where this resistor is. I'm going to suspect the resistor could be, or the corrosion could be at the switch. So I'm going to come over and I'm going to test right there on the switch. So I'm going to go and start the simulation again. Notice I have 8.86 volts. So now my source voltage is actually changed, okay? I think it was 872. I don't know what the heck it was earlier, but it seems to be a little higher. So what that means is my source voltage is actually greater. That's insignificant to my point, but that means that this voltage and this voltage are probably the same. I mean, I could test that if I wanted to. Let me just go ahead and check that. So let's go ahead and check this again. I'm going to come all the way over here. I'm going to come right to my, not my negative terminal. Now, if you get screwed up doing this, you can just click off of it and then start over. I'm going to come back over to here. I'm just going to go ahead and run this again. Start my simulation. See my 886. So that's a really good, that's a good read. So at this point, I'm suspecting my connector issue is somewhere between here and here. It's in this connector, okay? Now, if you've got a connector somewhere else, or you've got resistance somewhere else, we can verify it here. So I'll go ahead and do this. Start my simulation. And there's my 886. So my reading's good here. So I'm good. good, good, bad. So between your good and the bad is where your problem is. So I'm going to stop simulation. I'm going to rerun that wire, and I'm going to test to the other side of that resistor, and I'm going to read it just like that. Okay, run this again, start simulation. Notice that see a significant drop across the resistor. Okay, guys, that is called voltage drop. That's the most effective way of finding a resistor within the circuit. Again, it may be a little time consuming, but it is actually not time. Why did I say time consuming? It's really not time consuming. It's going to be the most appropriate way of testing and trying to find. Now, if you had to disconnect this connectors on both ends and measure resistance across, I put a 50 ohm resistor in there, and that's what we've been playing with. You're not going to measure 50 ohms on corrosion. You unplug the circuit and you take the current away, that connector is going to cool and that corrosion is going to make contact. It's going to measure good. Your ohm meter is going to throw you under the bus. So I would not even measure resistance across the circuit. If I notice the voltage drop on the feed side, I'm going to try to find it. And at that point, I'm going to replace whatever component it is. If it's a connector, if the wire, whatever the case may be. Okay, now let's stick that same resistor in. Let's see if I can find that resistor again. And we're going to stick that in. I think it was 50 ohms. Let me go back. And I'm going to grab this resistor. I'm going to stick it right here. I'm going to change this value to, again, 50 and go to ohms. And I'm going to go right to 50 ohms. Okay, so what I'm going to do is disconnect this. And I'm going to go black. Take that lead here. Go right to the resistor. Bring that resistor over. Okay, we're going to wire the bulb again. All right, there we go. We're basically looking at the same problem. So the bulb is going to be the same. The problem now is the problem is actually on the feeds, or excuse me, on the ground side. So what I'm going to do now is I'm going to take my lead. I'm going to stop my simulation, and I'll put my lead right here back to the feed side. Okay, coming into the terminal, and I'm going to go ahead and start the simulation. So 8.86. So I have full source voltage coming into the bulb. So the bulb is good. Okay, the feed side is good. Then I'm going to go ahead and stop simulation, and I'm going to check voltage drop on the ground side of the circuit. Right there. So let's go ahead and start that simulation again. Notice you got 4.52 volts on the ground. So what that means is there's an electrical potential or difference between this point, which should be ground, and this point, which is actual ground. And the electrical difference or potential is 4.52 volts. That indicates resistance in the ground side. Again, that is what we're dealing with. Now, I can't emphasize this anymore. A lot of people will say, well, couldn't I just disconnect the wire and measure resistance and find that resistor? No, because this resistance may only appear in the circuit when there's current flowing through the circuit. If it was there all the time, I wouldn't even be teaching a course. You guys would just turn your meter on, measure resistance of the wire, find it, and fix it. The problem we have is the green corrosion that's created by oxidation, rust, corrosion, whatever the hell you want to call it. The stuff that grows on our connectors and grows in our fuse boxes and grows in our copper wires that are bare varies, and it varies significantly based on the current flowing through. So this is actually a variable resistor. This guy can change. This may actually be 0 at some point. Okay, or may change to 100 at some point, or will be 25 at some point. And you see how the voltage is changing every time I change that number. Okay, and that's what happens. You get into a situation where it reads fine, then it doesn't. Okay, and that's what happens as corrosion builds in a circuit, builds and drops. So be aware of that. I'm going to go and stop my thing here. Again, I just felt like I wanted to put this little video together to help reinforce some of the things I taught a couple of weeks ago. There was a lot of information I covered with the students. It was a 6-hour class, 5 to 6 hours class. It was 2 nights. But I really think that this is something we need to revisit. We need to talk about more. And hopefully you got something out of this, and I hope this worked out for you. But I'm going to go ahead and stop this now. If you guys are interested in any more training, or if you guys are interested in any more training or videos like this, let me know if I can help you out. I think it's something we can revisit, we can talk about. So hope you guys are having a great new year, and we will talk to you soon. Thank you.